Yeah, I was saying that week 2 should be better than week 1. No? You prefer Sejarah, BM, Moral Agama? Really? Oh,
Week 1 model was the highest. Model was the highest.
I would prefer week 2. Week 2 is just bio and physics and maths, right? Sure lah. No, I'm joking. Okay, I know that you guys are stressed out. Okay, so our goal here is to just make these 2 hours as productive as possible. I know now your time is more precious than ever, right? Okay. Hi, you love week 2. I think most of you, okay, maybe about, yeah, just put it on the floor. Yeah, I think about half of you are my students, and maybe half of you have seen me maybe one time at least. If you don't know me, my name is Brian. JY, Mr. Handsome Boy, can you close the door for me, please? Thank you. Okay. Today we are going to tackle chapter 5 lah, right? My style is that I don't want you all to just learn very surface and then just know a bit and then go and sit for exam. I don't like to teach like that, right? If you want to learn something, you learn it very well. Let's take that knowledge and bring it forward until SPM so that it's useful until then. Huh? Okay, right. So hello, 80 of you online. Let's start. I'm going to start with gravitation. Very quick one. Gravitation only has 3 subtopics. Okay, gravitation only has 3 subtopics. Faster, take and sit down. Okay, 3 subtopics. The first subtopic, I will not go through too much. I won't even go through. If you want to, you can look at the last seminar I did went through a bit. I did summarize the whole 3.1 for your midterms, and now it's finals already. Hello, you take your notes here, and anyway. Okay, so this is going to be 3.2 onwards. We will straight away go and look at the first question. If the shaded areas are the same, or you know what, just for fun, relax a bit. I ask you a not so relaxing question. What did you all learn in refraction of waves? I think my students know where I'm getting to. But what do you learn in refraction of waves? Like the highlight. Yeah, the bending. Change of speed, that is correct. Change of speed. And usually in refraction, let's say for water wave, we normally talk about the difference in depth, right? Difference in depth. My students would know this. I always say this. The greater the depth, the greater the speed, the greater the wavelength, right? Okay. Today we are going to learn how come, not learn lah, revise lah for my students. We're going to learn why velocity would change when it's refraction. We are also going to learn why wavelength would change and why frequency stays unchanged. Okay, if you are one of those people who just blindly memorize, oh, for refraction, this one go up, this one go down, this one unchanged, and then for reflection, this one unchanged, this one unchanged, this one unchanged, one day your brain is going to fail you. And because you don't have a strong enough knowledge, I want you to try to learn chapter 5 with the least amount of memorizing, if possible. You already have so much to memorize for bio. Let's not do that to physics. Physics is actually very logical. I got one more question. If we say more obvious diffraction, does that mean the wave is weaker? More obvious, or sometimes we say significant, more significant. Is it a weaker wave or a stronger wave? Okay, who think weaker? Who thinks stronger? Who don't know? Of all people, you raised two hands. Okay, if in your head you are thinking, if you are thinking stronger, it is not stronger. Yeah, those who say weak, 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 very good. All my students. We'll see. Okay, I'm gonna get to that later. Okay, so we're gonna cover all this. If you still are in doubt a little bit for the slightest bit, today we're gonna cover all of that and make sure that you go home knowing very well what this more obvious diffraction means. More obvious diffraction means that the waves are weaker, not stronger. Weaker. Okay, we'll start with this question. Quick one, a bit of gravitation. If the shaded regions are the same, oh, there are 5 Nicholas here. Oh, yeah, I don't know which Nicholas is. I didn't know Nicholas was such a common name. I don't know, there are 5 Nicholas online. All right. If the shaded regions are the same, compare the time from A to B. Let's say you're a planet, moving from A to B and C to D. If the areas shaded are the same, can you compare the time? Got 3 answers only normally when it comes to compare. Somebody is higher, somebody is lower, or are they the same? What say you? Compare the time from A to B and C to D. A to B looks, oh, I know, A to B looks longer, right? So the time from A to B is longer. Okay, good job. You had one thing to learn in Kepler's second law and you got it wrong. Time is the same. Okay, we just write down. So the time from A to B is equals to the time from C to D. Okay, I'll finish 1, 2, 3, and then we talk about the law. Number 2, compare the speed of planet from A to B versus C to D. Who is faster? We just found out that the time are the same, right? We found out that the time and time are the same, okay? But your eyes are not lying to you. It is traveling more distance here, traveling further, but with the same time. That means it has to be faster, okay? Yeah, so the speed there is, you get it not? Same time, but in the same amount of time, I can travel further. Meaning I'm moving faster, the planet is moving faster. Can anybody tell me why? Why is it faster? Also got logic one. The simpler explanation would just be because it's closer to the sun, it has a stronger attraction force to the sun. You want to, you can draw this up, right? It is closer to the sun. When you are closer to the sun, you are attracted more to the sun. You have a stronger force or stronger gravitational force, which means you are also going to move faster. Okay, which means you're also going to move faster. Further means like this lah. Like this is further. Okay, so question 2 is distance. So I say, okay, distance of arc AB is greater than CD. AB there is moving more, that arc is a bigger distance as compared to CD. But if I compare the speed, so same time, but you move more distance, which means you have to move faster from A to B, right? The speed from A to B is greater than C to D. And this is Kepler's which law? Third law, okay, wrong. A lot of people will write third law, but it's actually the second law. How many Kepler's laws are there? Okay, in exam, right, guys, you write in English, right? I write greater because you guys know me, I'm usually in a rush when it comes to seminar because I'm usually very greedy. I want to do this, I want to do that, I want to teach you so many things, right? So I write short form a bit in the seminar, but in exam, you write proper sentences, okay, like how you would normally do in school, in class. Okay, Kepler's second law. So there's only three, you find ways to help you to remember. For example, if you want to, you can remember the three laws by, give me a moment. Guess what's this? It is a pineapple. Coconut? You had one job. Okay, it is. Okay, let's think of this. Eat a pineapple. Okay, why do I say this? Why do I say this? Because the first law is saying, all it is saying is that your orbits are in a elliptical shape. Okay, and A is talking about Kepler's second law, which talks about how their areas are the same. So the moment the question says area are the same, the time will be the same. That is what second law is saying. If the area is the same, the time is the same. Okay, second law. P stands for what? Not pineapple. Nothing related to pineapple at all. Period. Period means time. Period means time. The time taken to travel one round or go around the sun, for example, or go around the earth. Okay, so make no mistakes when they give you first law, second law, third law. If they ask you that question, first law, second law, third law, eat a pineapple. Elliptical orbit, area, period. Find ways to help yourself to remember, right? So next one, we look at the next thing here. Okay, so the moment you see they give you shaded area, same time, it is area already. Second law, not third law. Always people will write third law. Okay, compare the orbital radius of ISS and the moon. ISS is in short for International Space Station. Okay, so that is our radius. It orbits around here with a certain radius. And also, the moon orbits around the Earth, we know that, with a certain radius. Okay, I think to make life easier, let's call this R1 and R2. Right? And we are also going to have T1 and T2. Okay, T1 and T2. T stands for the period. How long it takes to go one circle. Okay, period is for the time taken to go one full circle. So we start with answering the first question. Very easy, this one. If I ask you which one radius bigger, R2 bigger lah, right? The moon further. Okay lah, I put like this lah, moon bigger than ISS lah. Okay, I scared later you don't know what's the R1, R2, you didn't label the R1, R2. Then you look back, you don't know what you wrote. Next one, orbital period. You think you use logic a bit. If the radius is longer, right? Do you think it will take a longer time to go around? Yes. Logical. Don't need to memorize, don't need. That means moon will take longer because the circle is bigger, Moon will take longer. I like question 3. Question 3 came out in, actually a lot of the questions, right? The concepts are tested in the last round's finals, meaning last year's Selangor paper. So instead of doing questions, I would rather I make sure your concept is so strong that any question they throw at you can answer, right? If I ask you to compare the value of the T squared divided by the R cubed for both the moon and the ISS, Who is bigger or smaller, or are they the same? What say you? This came out in one of the objective questions. Same? Really? Handsome boy, what do you think? Think? If you guys do not know why is it the same, let's think about what is given in the formula sheet. Usually they give us this. And they don't leave it like that. They equal it to another t squared and r cubed. Which means I can keep on equaling another t squared and r cubed, and they are always going to be the same. For the ISS, for the moon, for any other thing that orbits the Earth, it is going to be the same value. Same. That's why we can equal. Okay, got reason why we use equal sign, because really it is equal. Okay, so you say that this one you can start a bit. The t squared to r cubed value for the moon and ISS, you can say are the same or are equal. Physics law, if you are comparing the time taken, the period, Kepler's third law, right? Pineapple is period. Is area. It is elliptical orbit. Okay, so this is Kepler's third law. So remember, a t squared over r cubed is actually just a number that is the same. Okay, if it orbits around the Earth, whatever ISS, moon, or a satellite that orbits around the Earth, it is just a number, a fixed number. I think if I write a fixed number, you guys understand better, but normally we like to call it a constant. Okay, a lot of people are very afraid of the word constant. Just a number, guys. A fixed number. Okay, sometimes we like to call the constant a K even. You see exam like that, you don't get a shock of your life. K just is a number, right? Fixed number. Kepler's third law states that the orbital period, the square of the orbital period, is directly proportional to the cube of the orbital radius. That's all it says. In short, like that. Okay, the alpha symbol means directly proportional. How many of you here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, there's 114 of us. Okay, let's continue. If a radius of the Earth, radius of mass is big M, radius of rocket is small m. Okay, can you just write out the formula of escape velocity for me? The formula. I just need the formula. So you can, if you need formula sheet, I can give you this. Yeah, you pick one. It's somewhere here. Which one is it? Is it number 5? Number 7? Number 9? Which one is it? Okay, what is the difference between 7 and 9? Yeah, number 7 is the linear velocity. The velocity at which your moon, your satellite, anything orbiting around the Earth, that is that constant speed that is moving at, is this. But if you want to escape the Earth, then it's number 9. Okay, they won't tell you which is which lah. And their difference is so subtle. It's just adding a 2 there, so you don't mix up. Huh? Number 9 is escape velocity, right? Okay, so our escape velocity V is equals to, according to the formula sheet, it is 2gm, capital letter M, please, divided by small letter r. But I can replace small letter r to a big letter r. Next question. What is small letter r? What is big letter r? Okay, big R I already know lah. Question gave radius of the Earth, big R. Okay, radius of the Earth, that is big letter R. Small letter r talks about the total distance from the center to the center. So let's say my rocket is here. Okay, then we call this as the small letter r, right? But remember that for escape velocity, usually we are looking at the surface of the Earth. Okay, looking at the surface of the Earth. Because if you want to escape the Earth, right, isn't the surface your first escaping point? If you want to go out of the Earth, where is your first escaping point? The surface of the Earth, the ground, right? The surface of the Earth. So for escape velocity, we always look at from the surface of the Earth, and therefore you can just use the radius of the Earth to calculate the value. Okay, question 2. I like question 2. Question 2 came out a whole structure question last year. Selangor paper. If a bigger mass of rocket is used, state the changes to the escape velocity. Very good. I heard decrease. Very good. It is no change. And you're like, how they know no change? Did they memorize this? No, they did not. You just take a look at your formula. And what is the mass of the rocket? Small letter m. Okay. The bigger object, which is our Earth, is always big letter m. Smaller object, always small letter 1. The rocket is small letter. Do you see small m in that, in this formula? Yeah, just check your formula sheet. You see, don't need to go and purposely memorize. When in doubt, I would like you all to try your best to depend on the formula sheet. Some things can depend on. Then don't need to memorize already, right? No change because there is no small m here. Small m is the mass of the rocket. Okay, question 3. So a lot of people will write, oh, bigger mass of rocket, then the escape velocity bigger, like that, because they think mass is inside them, right? But you need to know what mass is that. That is mass of Earth. Number 3, if the rocket escapes from a planet with a smaller mass, state the change. Now you escape from a planet which is smaller mass. Look at the formula again. Lower, right now. It will decrease. You know why decrease or not? You know how to see, if I got the formula like this, now mass of rocket is who? Big letter M on top, V on top. What happens? When they are both on top, on different sides of the equation, they are going to act in a similar manner. They are both going to increase the same way. All right? The R, the G, they are constants. G is a fixed number. So is R. The radius of a planet don't change, right? So it decreases. Next one. At what position is the escape velocity measured from? Surface of the Earth. Okay, understand that the surface of the Earth, you want to escape somewhere, my first escaping point is the surface. First escaping point. Okay, that is your first escaping point. Question number 5. What is the definition of escape velocity? Now that you have done all of these questions, this would become easier already. Okay, let's think about what is escape velocity. The minimum velocity to escape, right? But when you write it out properly, it's a bit longer than that. The minimum velocity. Don't sigh, Kelvin, you're just starting. needed by an object. Okay, that minimum value that you need for an object on the surface of the Earth. Why surface? Because that is my first escaping point. To do what? To escape lah, right? To escape, what force are you fighting against? Gravity. You're fighting against gravity, gravitational force. You don't write fight gravity lah, right? A better word for it, we England a bit, to overcome, yeah, the gravitational force. And escape into outer space. Why does it decrease? Someone asked about question 3. When the rocket goes away from a planet with a smaller mass. You see, smaller mass of planet for number 3, meaning that your m is going to decrease. Your m is on top of this equation. Your v is also going to decrease. Okay, because it is also on top, at the top of the equation. Right, so there are some key highlights. It is the minimum velocity. To do what? To fight gravity and to escape. Where is it measured from? Surface of the Earth. Okay, now we enter chapter 5. So if you really understand the definition, I feel even if you really want to memorize it, at least you know what you're memorizing, you see. It's not like you're just remembering words. Very hard, right? You're not just remembering words. They actually have a meaning, right? Minimum velocity, blah, blah, blah. Okay, we look at chapter 5. This first question, very similar one, came out last year's finals also. A short structure question, I think it was question 2 or 3. The baby cradle is moved up and down by the mother. What happens to the oscillation when the mother stops moving the cradle up and down? There is one best answer, and many people don't know what is the keyword to write. What happens to the so you move the cradle out, right? The baby's inside, you move it, and it's oscillating up and down. But when the mother stops moving, what can you say about the oscillation? What reduces?
Energy.
Yeah, the energy does reduce, but the best word is amplitude. Yeah, the best word is amplitude. Okay, so this is the best answer they want. 2 words only, you get your mark already, right? You can write longer below the oscillation, the amplitude of the oscillation decreases, for example. Number 2, what is the name of this phenomenon? Damping. And if you are thinking, what the hell is damping? The most important thing about damping that you must know is just this one thing. If you forget everything about damping and you just want to remember just one thing, this is it. Damping is all about a reduction in energy or amplitude because there is some loss in energy, right? Loss in energy maybe because the spring got some heat there and stuff. There's some loss in energy, right? If the mother stopped moving the cradle, the baby will start crying. Okay, you can write that, no problem. Go ahead. Can I say the oscillation reduces? Cannot. Not specific enough. I want to see the word amplitude. We want to know that you really know this is talking about damping, right? That's why the word amplitude is important. Number 3, sketch a displacement time graph for this phenomenon. Wait, why suddenly got chapter 2 displacement time graph in here? A lot of people got this wrong as well. You all roughly know how it looks like or not? Yeah, it go up and go down one, but the amplitude decreases. Guys, amplitude is, okay, let's say this is the middle level, right? Amplitude is how low or how high the cradle moves. Okay, so it doesn't move as high or as low anymore. Okay, take out your ruler, draw down, draw like that. Displacement is in meters and it's against time. Let's put seconds lah. It's just a sketch lah, right? It's just a sketch. But can you just go and roughly segregate the same gaps? Okay. You can just like put like one cent, for example. And you start drawing your wave. You draw lah? I want to see your draw. You know, a lot of people forgot that the displacement, because this thing is moving up and down, the displacement will go up and down, up and down, up and down one. Okay, it is going to go to the highest point and then come back to the middle. Oh, sorry, not so sharp. Come back to the middle position. Yeah, and then it goes below its middle position. Okay, but you see, as I draw, I am going to consciously reduce its height. So 2 marks you are going to get for number 1, a reduced amplitude. That means the wave must get shorter and shorter and shorter and shorter. That is the highlight of damping. The amplitude that's swinging must become shorter and shorter and shorter. And also, it must be a constant period. Okay, constant period, that means the time for one wave, every wave must be the same. That means from here to here is one wave. This time is called the period. From here to here must be the same. From here to here must be the same. Okay, so the paper 2 last year, they asked to draw this, and many people couldn't do it. I'm the Picasso of physics. Oh, wow. What is SM? Okay, S stands for displacement. S is the symbol for displacement. M stands for meter, the unit for displacement. Okay. Can the height gets shorter, must be shorter and shorter and shorter. Okay, I like question 4. So they asked this last year. There is one best way to phrase it, but I wonder what will you all say? What should the mother do to maintain the movement of the cradle? No. Yeah, I know where you are getting at. I know where you are getting at. No, more direct. Add a motor, push once in a while. Okay, somebody say push once in a while. Someone say add external force. You're getting close. Pull the cradle downward again. Yeah, we pull it so hard and let go. No more baby, right? Solve the problem. Okay. Yeah, the keyword is periodic force. Okay, we apply. This is the best answer. You apply a force from time to time. Okay, periodic means, it just means apply force from time to time. Periodic means for a while you swing it a bit, for a while you swing it a bit, because the system constantly loses energy. So what you do, you constantly give it more energy, right? You apply force from time to time. And when you do that, you are going to get a graph that would look back like this again. For example, the amplitude will be maintained again because you are restoring that energy that is lost. Huh? Okay, let's move on. The cradle is not a slingshot. Don't do this to the baby at home. Thank you very much. Okay, you look at this diagram, can you all immediately tell me what phenomenon is this? Resonance, very good. The same question they asked last year. I think a different set. I think one set they asked the baby one set they asked this pendulum one. They say when X is oscillated and the other pendulum start to oscillate, which pendulum swing at maximum amplitude? What's your answer? M, okay. M will swing at maximum amplitude. Explain why 4 marks. I need 3 more points at least. They are the same length, very good. Very good. The keyword here is that they are the same length. And I'll explain to you in a bit why is it so important that they must be the same length. Okay. It's not that the rest are not swinging, you know. Everyone else will swing. You don't fight, huh? So because X swings, X will also swing this benang, this thread, right? And everyone else will start to swing. Okay, everyone else will start to swing, but M would swing the most because M has the same length. They are the most similar. And why is that so important? Because when you want to swing something, you must swing it at a frequency that M wants to swing. Okay, J is very short, right? So if you push it to swing, it would swing quite fast. N is very long, right? So when you push it to swing, it would want to swing with a longer time. So every different pendulum want to swing at a certain frequency. Okay, but only X can match it. You need to match the frequency. And that is very important. We say that the person moving it, the driving frequency of X is equal. Why we say driving? Because X is the one that makes everyone else move. It drives everyone else, is equal to the natural frequency. I explain natural in a bit. Okay, let's highlight a few very important things. Maximum amplitude, same length, frequency, same or equal. Resonance happen. You see, there is a reason why damping and resonance are in one topic. Damping talks about what? Amplitude decrease, right? Resonance talks about what? Amplitude is maximum, you know? Amplitude stays at maximum, right? It's because somebody go and give it the force, give it that periodic force, apply the force from time to time. X is applying the force from time to time. And X and M, right? Because they are so similar in length, their frequencies match, and they will start to also swing at maximum amplitude. And that is why resonance occurs. Okay, so if they ask for 1 mark explanation, you just say same length will do. If they ask for more, you can talk about its frequency, you can talk about resonance occur. Okay, a driving and force frequency is the same. Driving and force frequency is the same. Someone asks, gravitational acceleration is calculated from the surface of the Earth and not the center of the Earth. Really? Let's take a look. That is gravitational acceleration. It is measured from the center of the Earth. Right now, it is measured from the center of the Earth. You want this value, then it's measured from right now. You're welcome. Okay, so someone asked, is driving frequency and force frequency the same thing? Yes, they are the same thing. Okay, they are the same thing. So their frequencies must match. How do they match? They must look the most similar. Okay, same length. Number two, what phenomenon involved? You can write one more time, resonance. We already answered just now. Number three, I think I write here, number three. State and briefly explain a real life event on this phenomenon. There's one very important event for resonance, real life one, that happened. Remember that bridge? Yeah, the Tacoma Bridge, correct, the Tacoma Bridge. The collapse.
Yes.
Wait. The collapse of Tacoma Narrows Bridge. Okay, I don't think you need to memorize this, but just know that this bridge exists, right? It is a bridge built in the 1940s in the US, where it is a suspension bridge. That means it's suspended on two ends like that, and it can swing, you know. So one fine day, there is this very strong wind. There's this very strong wind, which is the forced or driving frequency, that could match the frequency of the bridge. So the bridge want to or have a tendency of swinging in a certain frequency, and the wind could match it. So when their frequencies match, what happens? The bridge also start to swing, and it's going to be more and more vigorous to a point where, you know, the bridge is not built to swing sideways. So what happens when it swings too much? It collapses. And it's in the 1940s lah, so maybe engineering at that time not so good yet. Okay, is equal to, yes, very helpful, to the natural frequency of the bridge. The bridge oscillates at maximum amplitude and collapse. Sorry, I was getting very far, due to resonance. And if I go and highlight the words, right, you will notice the points are the same. The key points are the same. I highlighted maximum amplitude in part one. Here also I highlighted maximum amplitude. So guys, when you answer physics questions, know what are the keywords they want, you know. You'll be looking for those words. I want to talk about resonance. I should talk about maximum amplitude. It swings a lot, okay? I want to explain about how their frequencies can match. The frequency doesn't come from pendulum X this time, it comes from a wind, right? Breaking of a glass due to loud sound. Somebody asked, how do you break a glass with a, not a loud sound, a very sharp sound, a soprano, very high sound, which I accidentally make at the start of the class, right? I think that, okay, if I sustain a very sharp, pitchy sound for a long enough time, and the frequency of that sound is able to match the natural frequency of the glass, the molecules of the glass will start to gain that energy and start to vibrate to a point where the vibration gets so vigorous, it cracks. That's how the glass breaks up. Yeah, like opera singer. Yeah, I'm not an opera singer. Don't try. Okay. Next one. Can you tell me what is the reflected angle? This is reflection now, right? This is reflection. A lot of people would say 30. If you think 30, it's okay. From now on, any angle you want to find in any diagrams, please always draw a normal line. Make sure you have that. Any angle, whether it's chapter 5, whether it's chapter 6, it's always from the normal line to, let's say, this source, 60. According to the law of reflection, there is such a law that says, if you go in and hit 60, it is going to come out also at 60. The reflected angle is 60. Okay, simple question, but I think it's a good reminder for a lot of people because they can ask you a very simple calculation. You know, in chapter 6, they ask you for sine I over sine R. Got angle there. Reflection also got angle. Refraction also got some angle. So any angle question, look for the normal first. Draw the normal first. Okay, normal is a line 90 degree to the boundary, the surface. 90 degree meaning a T shape. Someone asks, is amplitude related to energy? Yes, amplitude is directly related to energy. When we say amplitude higher, more energy. Lower, less energy. Okay, amplitude and energy, they're almost a word that can interchange. Number 2, state the changes to the reflected wave in terms of its V, F, and lambda. Can you tell me or not? They like to ask this so much in objective. Reflected wave. So the wave, we call this the incident wave. Hit the boundary and then gets reflected. During the reflection, if you compare to the wave before, do you think the speed changes? Okay. Do you think the frequency changes? Wavelength? Okay, good job. How do you all remember? Do you all just memorize? Okay, why does the speed not change? Or when does the speed change? Okay. I'm going to talk about it here. If I ask why does the V change, right, or when does the speed change, and you have no answer, it means that you're not very good at waves. Okay, and we are going to tackle that. That's why I put a double star here, and we're gonna deal with that. Okay, because a lot of phenomenon talks about that, right? So the speed doesn't change. The speed doesn't change. The frequency doesn't change. The wavelength also don't change for reflection. I'll explain why in a bit. Yeah, it is in the same medium, correct? So therefore, and which means there is no refraction, right? Therefore, the speed is the same. Reflected wave, speed, frequency, wavelength. Do you notice so happen they are all the things in your formula V equals to F lambda? All of them are unchanged. Always remember, speed only change when it goes to a different medium. When, let's say, light travels from air to glass, a glass block, speed will change. Light will slow down. Let's say light enters from air, it enters a pool of water. Speed will change. Different medium will change, okay? Different medium will change. Frequency will change when the source changes. Maybe you replace this wave. Maybe originally it is sound wave. You replace it with microwave, for example. You change the source. You change it to another wave. But kawan-kawan, this wave and this wave are the same, right? So their frequencies depend on the type, the source. It's the same wave. The frequency is the same. And if V and F don't change, wavelength don't change. The wavelength depends on the V and F. Okay. Later I'll teach you again how to see. Number 3, the wave produced in air is allowed to enter water instead of hitting the reflector. So this one is hitting a reflector and bounce. What if we let it enter like a pool of water? Okay, what happens to the speed, frequency, wavelength? Increase. All decrease, or is it just some of it? Okay, refracted wave, I write short formula V, and then there is the F, and then there is the lambda, right? For V, it decreases. For lambda also, it decreases. For F, is unchanged. When you go to water, right? When you go to water, the wave would slow down because it's harder to travel in water. For example, light. Light would travel slower in water. It would slow down when it goes to a different medium. It might slow down or speed up, but the speed will definitely change when you go to a different medium, right? So if you go to water, speed will change, and speed directly affects the wavelength. Okay, speed and wavelength, same one, how they behave. If one go down, the other one will go down. Frequency depends on the source, remember. The same wave go into water, same wave what? Before and after go into water, it's still the same wave. Unchanged. Frequency is unchanged. Okay. Number 4, state the phenomenon involved are refraction. Okay, not easy. Okay, before I move on and explain to you how one affects the other in the next part, let's not forget, please don't forget, all angles are always from normal. Please be careful on that. Confirm got some angle you need to get one. And they like to give you the wrong angle always. Okay, don't fall into the trap. Okay, this is when you will get a better idea of why one change, why one don't change, and why reflection like that, refraction like that, so confusing. Let's just use this using V equals F lambda. Explain when will V F lambda change, and how do they affect one another. So we got V equals F lambda. Can everyone here rearrange so that lambda becomes alone on the right side? Okay. Why wavelength decrease? I'll explain in here. Okay. Why does wavelength decrease? I will explain in here. Okay. I need you all to understand, even though lambda alone like that, it is on top. Is lambda over 1 on top of the fraction. Okay. So also another thing, V will affect the wavelength. F also can affect the wavelength. So the wavelength depends on V and F. That's why I asked you to arrange like that. It's more meaningful if you arrange it like that. So we call lambda as like, if you do experiment, we call lambda as the responding variable. It responds to the changes of V and F. V change, F change, lambda will change. Okay. When I finish this page, I'll give you a break. Okay. Your break is coming. Hang in there. Okay, but this is very, very important. Now, first thing, please know when will V change. V only changes when the wave enters a different medium. Very important, this one. Different medium or different water depth. Okay. And this is what? When you go to a different medium, you go to a different water depth. This is called refraction. Guys. Okay, like just now, sorry, what's your name? Adrian.
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 Adrian. Okay. Adrian. Okay. Not Kaijun. Don't confuse me. Oh, okay. Yeah, like just now you said refraction. Exactly that, refraction. Okay. And also another thing, when velocity increases, the wavelength is going to, can we take a look at the formula? Don't need to memorize one. V is on top, right? Lambda is also on top. When both are on top on different sides of the equation, V go up, lambda go up. But will F change or not? Okay, so you must know anytime the questions say go into a different medium, air go to glass block, for example, or deeper water depth go to a shallow water depth, for example. That is all refraction. All of that speed will change. Okay. Another one would be, when does F change? F only changes when the wave source or the wave type changes. If you change to a different type of wave. Okay, so for example, let's say I got reflection. The wave go in, hit a reflector, and then bounce off. It's the same wave, guys. Frequency won't change. The same wave go in from air, go into water. It's the same wave. Frequency also don't change. Don't memorize if you can. Use this logic. That means you really understand already, right? So, but let's say I change the type of wave. I change it to a different wave, for example. Okay, like from radio wave, I change to gamma ray, right? Frequency would be higher. It would mean that when the frequency of the wave does increase though, wavelength is going to go down. You all see not F down there, F down there, but lambda on top. One on top, one at the bottom is going to act inversely proportional. But will V be affected or not if I change the source? No, V is the same because V depends on the medium. F depends on the source. Don't mix up. Okay, there is a bit of space here. Can I draw? Okay, wait, you know what? Wait. Can I draw this? So I got a swimming pool that looks like this. On the left side is a baby pool. On the right side is a adult pool. You got a shallow and adult pool. And this is the depth. Okay, if we say that we got a deeper swimming pool, when the depth is bigger, the speed is going to increase. And when speed increase, the lambda is going to increase. Okay, this is a refraction also. Because I explained to you different medium, I think most of you understand that. But different water depth also will affect. How deep lah? You got a shallow water and a deep water like that. But their frequency same or not? The wave frequency here and here, is it the same? Same, right? Because it comes from the same source. Let's say you got an ocean, the same ocean wave. The wave before and after same. It's just that the depth is different. Source is the same frequency. Okay, be very good at this, please. Same frequency, that means frequency is also, if you go and arrange this, frequency is also called V over lambda. right? So sometimes you will see in some questions, they will ask you to go and compare the frequencies or the V over lambda of the shallow region and the deep region. Their values are the same. This formula is not given, but it's all very logical. If I know that the source is the same, it's come from the same water, just that it goes to a different depth. Frequency same. What's frequency? V over lambda. I just arrange only. Formula, that one given. Right now. So that means at the shallow region, the V over lambda is the same as the deep region. They are all equals to that same F, that same frequency. Okay, so if I ask you to do a calculation like that, got different speed, different wavelength, you can go and find out. In what case does the frequency increase? If you change the wave to another type of wave, okay? Or, you know, in school, I think most of you have done the experiment where you have a water dipper. Maybe I change the setting of the water dipper to create waves that move faster. I change the source, you know. If I make it move faster, the source change already. I know it's creating water wave, but the water wave produced now, that source is different, right? It moves faster. So anytime you're not going to a different medium, different water depth, or the source never changed, you don't simply say V or F or lambda change. Okay? Your school note. Okay. S and B. Oh, S stands for shallow. You know the shallow part of the pool. D stands for the deep part of the pool. Deep and shallow. Okay, one last question, and then I give you a 5-minute break. State the phenomenon involved. You answered a bit too fast, huh? Diffraction of waves, huh? Diffraction. Okay. A diffraction, if it's just diffraction, is fine. Okay? If it's just diffraction, also okay. Yeah, it's up to you, your preference. What is the word that what is the word that I can replace diffraction? Dispersion is a different thing. Spreading. Dispersion is when, let's say, white color light spread into its 7 colors. That is dispersion, which in our syllabus for physics, we don't really touch on. That one you all learn in Form 3, just the color dispersion. But diffraction is that spreading. Diffraction means spreading. Huh? Okay, state the changes to the speed, frequency, and wavelength. I think you should be very good at this. Does the speed change or not? The medium got changed or not? No. All I did is just put an obstacle there. I didn't mention the depth is different. I didn't mention the medium is different. So don't assume. Don't assume the speed is going to be the same. Right? All I did is just put 2 barriers there and let us put the small hole there. Speed don't change. Same medium, same depth. Frequency got changed or not? Okay, let me ask you a question. Is the wave here coming from the same place? It comes from the left side, right? Same source, right? So frequency don't change, right? Okay. So when V and F both don't change, lambda also don't change. I just write in short like that. V, F, lambda are unchanged. Reflection energy decreased a little. If they ask that, what do we write? Yeah, you can, Isaac, you can write that. So normally, right, when wave is reflected, the energy gets absorbed into the reflector a bit, right? You can say the energy decreases, you can say the amplitude decreases, Okay, but I really hope you guys know how to see. Same medium, same depth, speed don't change. The wave come from where? Same place, same source one. So the frequency don't change. Then the lambda also don't change. Question 3. What is it that changed? Amplitude. Very good. Energy also. Because they are same, right? Amplitude. You know how high your water wave, I imagine water wave. How high the water wave go or how low it goes depends on how much energy it has. So if the wave is very energetic, it will go very high. Very high. Amplitude is high. But if got no energy, this wave, then the wave will go very low. Okay, amplitude and energy. Hey, hey. Oh, you mean because of the direction, is it? Not the answer we're looking for, lah. Right? Not the answer we're looking for. Yeah, but I get what you mean. The direction doesn't change. Okay, can you all go and highlight this? And highlight this. Please understand, this tiny bit of the wave became this. Without any physics knowledge, just logical thinking. I could ask standard 4 the same questions, okay? So please answer or please think using logic, okay? That means you don't need physics knowledge to answer this, okay? For that same bit of wave, just this tiny bit of wave, and now it has spread out to such a big area, do you think it will still be as strong as before? Or do you think it'll be weaker? Need to memorize or not, these kind of things. Don't need use logic because so little part of the wave go in and then now it's spread. Spread, that means energy also gets dispersed, not dispersed, diffracted, spread out. Okay. And then this part left, some people ask what happened to here. It will just hit this guy and then it will get reflected lah. Okay, that one is not what we are studying in this question. Yeah, the wave become weaker, correct? Energy and amplitude decrease. Weaker is energy decrease. Okay, number 4. To produce more circular waves, state 2 changes that should be made. Do you know how after they pass through what is that hole called? A slit, huh? This hole is called a slit. Okay, yeah, you know how after it goes through the slit, it will spread, right? Okay, and it will become quite circular. To make it more circular, what should we do? Wait. Sorry, what do you say? Reduce the size of the slit. Is that what you say as well? Okay. I need you all to know this. If you want more circular wave, does that mean more or less diffraction? More significant diffraction or spreading. If it's more circular, it means that it spreads more. For it to spread more, it needs to be weaker. Okay, everyone is saying smaller slit. Very good. But it's really very logical, and I don't need you to memorize because, friends, if you know the wave is going to be weaker, how to make it weaker? I put the hole smaller, less wave pass through, then weak low. Logical, right? So the 2 answers would be, yeah, you can reduce the slit size lah. Okay, the size of the slit or slit size. That's the first one. What else? I can also use wave with bigger wavelength. Okay, because bigger wavelength. Bigger wavelength, that means the frequency of the wave. I use a different type of wave, by the way. That means the source changes. Big lambda, is it big or small frequency? Yeah, if you're not sure, you just take a look at this formula. When we say lambda is bigger, and I change the source, the frequency will go down. You all know smaller frequency wave means weaker. Okay. Frequency is actually directly proportional to energy. When there is a smaller frequency, it means that the wave is weaker. And where's all this heading towards? Weaker. As long as you know this, you would have no problem answering because it's so logical. How to make it weaker? Close up the gap. How to make it weaker? I use a wave that is weak from the start. Small f, big lambda. Okay. Number 5. This phenomenon occurred when the wave passed through a slit. Give another example when the same phenomenon can happen. When the wave passed through, and not only a slit, you can let it pass through an obstacle also. Like let's say a rock. Okay, and let's say you got some waves. Last year, got one objective question asked this. If the wave go like this, then it kena the rock, obstacle kan, it will bend around the rock like that. Okay, so it will spread around the rock. This is also a diffraction. Okay, we always focus on the slit one, but if they give you an obstacle, it's also called diffraction. It's also spread around the rock. Okay. So they gave this diagram and then they just asked what phenomenon, right? A, B, C, D, they ask like reflection, then you know the answer is diffraction. Yeah? A lot of people say reflection because the wave kena the rock and bounce back. Good job. When the wave passes through the side of an obstacle, okay, you can put an example like water wave passing through a rock, or you draw that rock lah also can. I asked you, if I put a slit so big, very big lah, right, as compared to the diagram, will it be more circular or how will it look like? Less circular, it'll be straighter. And what's the logic of that? Because you allow so much wave to pass through, it becomes a wave that is so strong that it won't even bend. It will just travel. Like, because so much wave get to pass through, it can retain that very high energy and it continues to move almost like there is no difference before and after, right? That's why it's so straight, because it's very strong. Okay, because it's very strong. If it's straight, then you will have a very strong wave. It's all very logical. You put the gap so big, so strong, then it remains as its straight line wave. It's not going to curve. Okay, so for more diffraction, you want weaker wave. Then you will know what to think it is. Close the gap. Use wavelength that is weaker. Okay, we are going to take a break. It is 5:46 on my watch. We'll come back at 5:51. Okay, I give you a 5 minutes break. Just rest your brain a bit. Go to the toilet if you need to. Okay, page 3. If the reflected waves are received at after 0.24 seconds, okay, read the question carefully. Waves are received after this. Sorry, there's an extra after. Or I should cancel the after before. Wait. Okay, this one after transmission. Okay, so what they do is to measure the depth of the seabed, they are going to send some wave down, hit the bottom, and then it's going to come up, right? So the reflected waves are received 0.24 seconds after it's being transmitted. What is the depth of the sea if the speed is this? What formula am I supposed to use? If you're thinking V equals F lambda, because that's like the one of the most important, or rather the most important wave equation, right? There is V, there is no F in here, and there's no lambda in here. Very good. Guys, it is actually simpler than you think. Just speed equals to distance over time. Right? I think this one, everyone got no problem. You all learn from primary school. It's just that sometimes we think too far and then we forget that, hey, there's also this formula, right? Speed equals to distance over time. So what they are saying is the wave is going to go down, hit the seabed and come up again. And the total time to go down and come up is 0.24 seconds. When they give the time, right, they would always give two waves. That means it will go down and come up again. Because you think logically, if I want to find out the depth of the seabed, I won't put a receiver down here. That means the timer will not stop when the wave go down. The timer will only stop when the wave go down and then come up. Right? If I know how deep it is, what's the point of measuring the depth? Right? If I know how deep it is and where to put my receiver, right? What's the point of measuring the depth? Okay, so we let it hit the bottom and come up always. Speed is 1500. That's what they say. The distance to go down and come up is 2 times of the d. You go down is 1 times of d. You come up again, 2 times of d. The time is 0.24 seconds. Okay, and you can times the 0.24 to the left side, and you can divide the 2 down, which is the same reason why sometimes they will tell you the depth formula is speed times time divided by 2. You will always need to divide by 2 because the time is always go up and come down. Okay. Yes, the time will always be the time to go down and come up. Okay, so this is reflection. Question number 2 and 3, right? This concept was tested in an essay question, compulsory essay question last year. Okay, quick one. You take a look at what they say. State the type and frequency of wave used to measure depth of ocean and satellite communication. Explain. What is the wave that we use to measure the depth?
Microwave.
Ultrasonic. Ultrasonic is the only answer. Okay, ultrasonic is the only answer. So it is ultrasonic wave. Ultrasonic is sound. Sonic is sound. What about for satellite communication? Is it radio wave or microwave? Okay, it is microwave. Do you all know that in microwave itself, there is a range, right? There's a higher frequency microwave, lower frequency microwave. I want the highest possible one. I want a high frequency microwave for satellite communication. Why don't we use radio wave? What's the problem with radio wave if you compare it with microwave? Yeah, radio wave is a bit too weak. The frequency too low. Always remember, the higher the frequency, the more energy it carries. Okay, the more energy it carries. Microwave is higher frequency, higher energy as compared to radio wave. If you need it to travel very, very far, you use a wave that is stronger usually, right? So if you compare between radio wave and microwave, that's the reason. And if I ask you why you want high frequency, you can say, okay, quick question. High frequency, will it easily diffract or not? Don't answer so fast. Think about it first. Diffract. For diffraction, we want strong or weak? We want weak for diffraction, but high frequency is strong. So when it's high frequency, it cannot be diffracted easily. And we think a bit, why is that a good thing? Why sometimes we want it to diffract? Why sometimes we don't want it to diffract? That you want to measure the depth of the seabed, right? You want it to go straight down and not spread like that. You want it to be so accurate that it goes straight down and come straight up. You want your microwave to reach the satellite. You want it to go straight to the satellite and come back. You don't want it to spread like that. We don't want the spreading. So the wave has to be strong. It has to have a high frequency. Yeah, okay. So it's all very logical. And then the next thing is they can ask you like if you want high amplitude or not. You say yes, I want high amplitude, because high amplitude wave also means high energy. So you can tell where this whole sort of essay question is going towards, just high energy, high energy, high energy. Because I don't want it to spread. I want it to go straight down to the ocean. Can you imagine it has to travel so much volume of water straight down to the ocean? We need a lot of energy to do that. It has to go so far, pass through the atmospheric layer, go to the satellite. Travel very far, you need high energy. And high energy will give you high penetrating power. Which means it can penetrate deep into the sea. It can penetrate through the atmosphere, that thick atmospheric layer. Don't memorize, understand the concept, understand why I pick a high frequency. High frequency because can penetrate like that. If you found that physics has a lot of memorizing, you're learning physics the wrong way. Able to penetrate a great volume of water or thick atmospheric layer. Okay, number 3 is very short. Now we look at a different situation. For ambulance sound to spread easily, or radio wave to be transmitted easily across the hills, like the diagram down there. Okay, the next diagram. For ambulance sound to spread easily, keyword is spread easily, radio wave to be transmitted easily across the hill. You know the wave, right? Even though it crosses a tall mountain like that, but this part can still spread. Okay, then now you think, oh, I need it to spread because ambulance sound, usually, right, ambulance sound, you just want the people around the ambulance to hear it, right? Do you need the ambulance sound to travel 1,000 kilometers? We don't need that. Do you need the ambulance sound to go deep into the depth of the sea? Don't need, right? You just want around you to be able to hear it. So you can use a weaker wave because it will then be able to, weaker means can diffract, can spread around you. So people around you can hear the ambulance sound, right? So this part, the wave also can spread, for example. Okay, so you say you want waves with lower frequency. Because lower frequency, you can explain by saying Lower frequency wave, that means it has a greater wavelength. Frequency and wavelength is the balik one. This is one of the things we want when it comes to more diffraction. You can say more significant or obvious wave diffraction. More spreading. Ambulance sound. That's why I purposely give you number 2 and number 3 side by side like that. I want you to be able to differentiate. You want it to spread, or do you want it to travel a very, very far distance? That determines the frequency. Do you want diffraction or not? That's why the idea of the entire diffraction thing must be good, must be stronger. Okay. Next one. Can I go and split this into half? One of it is 10 marks, meaning one of it is an essay question. I think I've given the answer already. This is diffraction, right? And know that it is this part. This part diffracts. If the wave is so strong, it will just pass through the hill and it will just travel straight. It won't come down like that. And the fact that it can come down, meaning that it is weak enough to do that. Weak, not strong. Okay. I saw one student just now send me a message. Some leak question. You know, I hate all these leak things. Your sejarah paper leak lah, this one leak lah, that one leak. Some people are saying physics will have diffraction. If it really comes out, I hope everyone will do well lah. Okay. What wave do we use for this kind of transmission of? Yeah, it is radio wave, not microwave, radio wave. If you compare radio and microwave, you look up again, microwave usually higher frequency, more energy. Radio wave, less energy. I use radio wave for things like shorter distance one, like, you know, local radio station, local TV station. But I use a stronger wave like microwave if I want it to go to, let's say, the satellite very far. Okay, number 3. Lignan, very excited. Okay. Number 3, what are required to give? You are required, to give some modification so that the residents can receive better TV signals. You can include this one. I copy from last year, the Form 4 finals also, right? It's in the compulsory section C. Frequency of the signals, which many people wrote higher. Think about this. This is diffraction. Frequency must be lower, weaker. Location of the transmitter. We'll go to that in a bit. Let's start with number 1, low frequency. Exam, you please put in table form. Okay, I write like that because save space a bit. When it comes to diffraction, you always want to say greater wavelength. Greater wavelength got more diffraction. Okay, low frequency can give you greater wavelength and more significant diffraction. Number 2, location of transmitter. This one where you put Oh. Yeah, at the top of the hill. Reason? Or rather, there is less obstacles if it's at a high position, right? For example, if I put a speaker on the floor, let's say in your school hall, the speaker usually hang on top one, right? If you put on the floor, then kena everyone's feet lah, right? Not then we'll have a lot of obstacles, right? So you can say high lah, right? High. For example, the top of the hill. wave signals are blocked less by obstacles. Number of transmitters, what will you say? More, free mark this one. If you say, I want 5, you're not going to get marked. I want 3, you're not going to get marked. More than 2, you're not going to get marked. Just write more, right? You're creating a best system, you know. More, greater number also can. Huh? If you got more, right, you can then spread further along. You can, each transmitter can diffract, and then you can spread to a wider area. Further, you want to add wider also can. Okay, further or wider also can. Or you write both. Strength of signals. I don't want you guys to confuse strength of signal with the energy of the signal. Even though when we say stronger, more energy means stronger, right? Usually, but when it comes to strength, it means like the number of signals. Like how many more signals do you have, right? So strong strength of signal. Like for example, Wi-Fi, right? You know, sometimes you guys get a a lot of bar of Wi-Fi. Sometimes it's very weak, right? That strong or weak, frequency same one. Frequency same. It's that same frequency of Wi-Fi. But how much of that radio, Wi-Fi is radio wave, by the way, how much of that radio wave are you getting? That determines how strong the Wi-Fi is. Huh? So strong strength of signal, which really just means you have more signals. And it's the same reason as before. To spread signals further to many areas, for example, we can elaborate a bit. Last one. Distance between transmitters. Strength of signal is, yeah, just how many signals. Distance between two transmitters. Closer or further? Further, then you have less wave, right? Closer, right? If you are, because the wave is already quite weak lah. So if you put them closer together, ideally lah, if you put closer together, it would mean that it can spread further. It can maintain that high strength of signal. I can make sure that there is a lot of signals at any distance. A lot of people lost mark in this 10 mark essay. They don't know how to write the frequency. They don't know where to write the location. A lot of people wrote the location near the house. Salah. A lot of people write the number as in 5 transmitter. They gave a specific number. Salah. Right? A lot of people don't know what to write about strength of signal, but most people got the mark here, even though they don't know what is going on. They just write, oh, strong lah, right? Definitely strong. And then distance, many people also wrote further. So a lot of people didn't even get half of the mark here last year. Okay, so I just want to give you guys exposure lah. Short distance between two transmitters. To maintain high strength of signals. I can keep on making sure that there are a lot of signals and it's very strong, right? So I put a lot of stations and got a lot of signals lah. What is the phenomenon involved? This is interference. What is the word that I can replace with interference? Oh, someone asked this question can do table. Please do table. In exam, please do it in table. Or the 10 mark one, please do it in table in exam. Okay. Yes, it is overlapping. What is one more word? Okay, so it is interference of waves. So diffraction is spread lah, right? Diffraction is spread. Interference also means superposition. Superposition also means overlapping. If you see a fancy word, superposition, it just means that the wave overlap. Quick question. For waves to overlap, how many waves do you need? 2. Okay, if you see one wave, don't say interference overlap with who? One person? 2% overlap. Huh? You need 2 waves to overlap. Okay, 2 waves to overlap. And you need a coherent source, right? There's the S stands for source. You need 2 of those to have that overlapping. Okay. And if they ask what is coherent source, which is very popular, last year SPM also asked definition of coherent source. It just means same, but what is same? Same frequency, and there is same phase difference, constant phase difference. Okay, I explain what it means. Okay, it means that you have source of waves with the same frequency. That means they are exactly the same wave. And constant phase difference. Okay, same frequency, you all know what it means, but constant phase difference, right, means the wavelength same, and also they overlap perfectly one. Okay, they will overlap perfectly one. That's what constant phase difference means. Because when we say in phase, that means that their wavelength is the same. Okay. If you write same wavelength, usually they don't accept because that is not enough, not specific enough, and it must overlap perfectly also. Show in the diagram an antinodal line and a nodal line. Okay, this line right here is what line? This purple color one that I drew. If you think, oh, it's the wave that is very calm there, it is antinodal, it is nodal. Okay, don't worry, I'll get to there if you are one of those people who always get confused, nodal, antinodal. Okay, that is a nodal line. And then antinodal, I just draw anywhere in the middle, like this. Many people get confused with the word anti. They ask what occurs at the nodal and antinodal. Someone asked what is the meaning of monochromatic light? Monochromatic meaning light that has one color and one frequency. Same color, same frequency. Yes, thank you, Carson. Number 4. So I'm going to teach you. If you find it so hard to remember node, anti-node, You know there's two types of interference, right? Constructive, destructive. I think everyone should know that. Okay, you tell me constructive interference happens where? At the antinode. Constructive meaning you have the same type of wave overlap. The English word construct means what? Build. You are building, English, you are building taller waves. So you overlap one tall wave with another tall wave, for example. You are building taller waves. Or you are building very, very low waves. The same kind of wave, they overlap each other, they would enhance each other. You are building stuff. Okay. And then destructive. Okay, give me a minute, I'll explain antinode node in a bit. Destructive interference occurs at the node. The English word destruct means destroy. And how do you destroy? Two different waves overlap. If it's all very logical for you, when you look through and when you answer questions, you realize that, oh, it's not too bad, right? Because you really understand what is going on. And all this can help you to explain and do any type of question they throw at you. So it's a wave that go up and go down. And when they overlap, it becomes flat. Okay, the one going up is called a crest. The one going down is called a trough. Let's talk about the word node. Okay, NO stands for no, yeah, NO is no. No is nothing lah, right? Nothing there. So when you see the word node, it means that there is no wave there. Because it has been cancelled out, there is nothing there. It's destroyed. It is destroyed. That's why nothing. Why got nothing? Because destroyed, no more wave there. Destructive. But if I add the word anti in front, what happens? Yeah, no destructive. It's the opposite. Anti means opposite of nothing. Okay, so if you see node, nothing, that means destroyed. Nothing is destroyed. Anti of nothing, opposite of nothing is constructive. Okay, question 5. So don't forget what is node, what is anti-node. They can ask you to point out, they can give you a diagram, put point P, point Q, and then ask you to circle objective maybe. Which one is it? Question 5, state what happens if a small piece of paper is placed at the node. At the node. Node, nothing. There's nothing there. Okay, there's nothing there. Which means that piece of paper is not going to move up and down, up and down, up and down. It is on top of a wave that is nothing. It is, let's say right here, this small piece of paper. It won't move. It will just stay there. Okay. The paper does not move up or down. It maintains same position, meaning same amplitude. It doesn't get any higher. It doesn't get any lower. It maintains only. The paper don't move up, move down. Just stay there only. But if I put on an anti-node, then it's different. It will rock up and down, up and down. Okay, I think we have time to do one last question, unfortunately. Always cannot finish a seminar. I'll give you the answers later, don't worry. But I think we achieve our goal. If they ask you any diffraction question, whether essay, whether structured, whether objective, I ask you interference, I ask you reflection, refraction, whether speed change, that change, that change. You'll be so good at it, you can answer anything they throw at you. I hope. Fingers crossed. Okay, next one. State what happens at the loud and soft sounds. You see two loudspeakers. Two for what? To overlap. Okay, so state what happened at the loud sound. Loud sound happens when you got constructive, right? Constructive. I'll just write loud sound. Constructive interference. Soft sound. The sound is destroyed and hence soft, destructive. Okay, number 2, 10-mark question. This sound system is used in a school hall. Normally, our hall don't just have one speaker, got a few speakers. If I put 2 speakers, what modification should be done so that the students can hear the sound more clearly? You can include aspects such as the position of the loudspeakers, distance between loudspeakers, position, microphone, material of one. Someone asked, teacher, where is the note? Note is anywhere on top of, okay, I give you some examples of note. This is a note, this is a note, this is a note, this is a note, because there is nothing there. The waves has been cancelled. All those are note. Okay, join them together, you get a nodal line. Okay. Where to put your speaker? Just now I already say you don't put on the floor, right? You put up there, right? Okay. You say high position. Or you can say close to the ceiling also can. Reason, sound not blocked by obstacles. You do a few, you get the hang of it, right? And then next one. Distance between the loudspeakers. Why? Why far away? Your aspect okay, but the reason not okay. Okay. This is the one that I want you all to take note. The second one is the most important one, actually. Okay. All right, first, greater distance. Some people think, teacher, why you want to put the speaker far away? Then later the students cannot hear. No, that's the wrong idea. We want greater distance between loudspeakers. Do you see the A in the diagram? That little A there? That is the distance between the loudspeaker. Okay, so we want to increase the A. That's what we are saying. We want to increase the A. What is the interference formula? Don't need to memorize. Given one. Okay, you all know what is lambda, the wavelength of the sound. A is the distance between the two loudspeakers. X is the distance between two loud sound, two soft sound, for example, or two note and antinote. D is the distance between the source and where you measure the X. D stands for distance. Okay. But same thing like your V equals F lambda, this is not very meaningful if you want to look for how they relate to each other. You know, V equals F lambda, I said that lambda is the responding variable, right? So it's on one side. So different things can affect lambda. But what do you think is the responding variable here? What is it that you change and can affect the results? We are changing A, we are changing the X, which is the lambda, which is the source. We're changing the D, right? And it all will affect the X. So please, let's try to move everything to the left side and leave X alone. Times the D up, divide the A down, and leave X alone. Very important. Calculation, no problem. You guys are good at maths, I believe. Huh? So you just submit, you find some value. I leave that to you. But a lot of people don't know how to get the relationship. That is more important, you see. X must be alone because lambda will affect X, D will affect X, A will affect X. X is the guy that is affected, the responding. So, and out of all of it, this is the most important one. When A goes up, X goes down. When A increases, the distance between the two loudspeakers increases, X is going to get smaller and smaller. The loud sounds are going to be so close that we want the loud sounds to be so close together, constructive interference so close together, that anyone sitting here can hear very clearly. If your loud sounds are very far apart, that means you have a very big soft sound gap in the middle. We don't want that. We want the loud sounds to be very close together. Get it? Loud, 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 loud. It's all very close together. So greater distance between loudspeakers so that you get smaller distance between loud sounds. Which means X will decrease. That is our goal. And people there will be able to hear it very clearly. Okay. Number 3, position of microphone. You put the microphone in front or behind the loudspeaker. Okay, if you put the microphone here, right? You are speaking into the microphone, and then the sound from the loudspeaker also go into the microphone. You will get disturbance. Oh, not good. You put it, you ask the speaker to, or ask the person talking to speak from here. Okay, so that the sound from the loudspeaker won't go into the mic. You know, sometimes in the school hall, you get some screeching sound. Not like that. That's not screeching. Yeah, microphone must be behind the loudspeaker. Sound from loudspeakers does not enter . Can I write short form mic to produce noise disturbance? Or if not, you will just hear echo of yourself. The sound keep on going into the mic from the speaker, right? Okay, and that is noise disturbance. Okay, last two. Last two is easy. They ask material of the wall. When you go into cinema, have you touched the wall before? Yes. You've never touched the wall of a cinema? Okay. One day you should go and touch it. When you go into a cinema, if you ever touch the wall before, it is soft. It is a carpet wall. Okay, or else you watch your favorite movies and the sound keeps on getting reflected, and you're gonna hear echoes of the sound. It's very loud, right? In the cinema, you need very thick carpet walls to absorb, so that there is no reflection. Use a soft board or a cushion material. For the wall. Because if it's a cushion, right, it can absorb the sound energy. And reduce reflection. So you won't keep hearing echo of the movie, for example. So same goes to your whole reduce reflection of sound. For the floor, you use the same concept. You can maybe put a carpet I'm sure if you have gone into the cinema, you have stepped on the floor at least. You haven't touched the wall before, never mind. You have stepped on the floor before. And it is soft. It is soft. Carpet as material of the floor. Reason, same one. Okay, the reason is the same. Someone asks, can I write loud sound and soft sound as nodal and anti-nodal line? Can the loud sound and soft sound as no. Loud sound and soft sound must write constructive, destructive interference. Okay, this one same reason to absorb sound, reduce reflection. Okay, question number 3. They say this phenomenon is observed in water. This overlapping in water also got, sound also got, light also got. Okay, state how this phenomenon for light can be produced. Yes, you know when sound wave, you want them to overlap, you put 2 speakers. Water wave, you want them to overlap, you put 2 water dippers, dip, and then they will overlap. Light wave, you put, or you use a double slit, a very tiny slit, or you say allow lights to pass through. Whether you want to write narrow or not, that's up to you, but double slit. Okay, I just want to remind you all that if you see a double slit, it is interference because light will pass through the 2 slits and they will overlap. Okay, one last minute before I end. Your electromagnetic waves, I don't know how you remember, but you can go by this. Very what? Useful?
Very useful.
Okay.
Yeah, very good. What I meant was very. Yeah.
And when you in exam, you don't have to write it out in sentence like that. Okay, if you have a way to remember it and it's stuck in your head, good for you. Okay, but if you need a way, then this is the way you can do it, right? Real money is very useful and extremely good. Right? I know extremely is not spelled like that. There is a missing E, but the sound of it is X, right? Radio wave, microwave, infrared, visible light, ultraviolet, X-ray, gamma ray. What if they give you the order terbalik? Then you write terbalik lah. Radio wave, real money is very useful and extremely good. Okay? So you have your waves already. But what does... You remember the order. You need to remember what is it for, you know. What is it for? This guy is high or low frequency? Lower. Low frequency means high or low wavelength. Then the rest you know already lah. From low, it will go to higher wavelength. Low to high frequency. From high wavelength, high lambda, will slowly get smaller and smaller and smaller. Like that. Okay, so that's it for today. The rest of it, I'll give you answers lah. There's a lot of essay questions that are included. I hope you feel more confident with waves now. Okay, I hope that. Yeah, and good luck for your exams. Good luck for your exams. For my students, I see you again next week. Bye.